And I will lead into the next presenter, which is Sandy Curth. Yeah, a couple of months ago, me and my wife we were watching the computer, I guess, not the TV, and we saw this great project of a 3D printed earthen architectural structure. I believe it was in relation to the winning of the 3D printing challenge, which we participated in as well, but lost to, amongst others, this project. Yeah, the rammed earth always has a bit of a dusty, or as we say in Holland, the goat wool socks image. This project really gives it a revitalized idea, and I think it's really important because the materials are very ecologically sane, and it makes a lot of sense. There's not a lot of cost to it, and everybody can do it. And I think this is, of course, also one of your focus points. Yeah, great to have you then in as a presenter in this session. You hold an architecture master at Berkeley University, and you're now a PhD student at the MIT Computation Department, a designer, computational researcher whose work focuses on the development of tools for a more democratic access to architectural additive manufacturing. You received many awards already, including a very impressive sounding presidential scholarship for MIT. And we share the experience of being having been part of the Norman Foster robotics workshops, which very interesting in Spain. He invites scholars from around the world to work on these environmentally interesting concepts of additive manufacturing or robotics applications in architecture. I'm very keen. I already have a couple of questions for you after the presentation, but very keen to see your story.
Thank you for the kind introduction. Can you hear me okay? I will screen share. So it's an honor to be here. I'm glad I can talk about some of this recent work. As we'll see momentarily here, it's a bit in contrast to the European Space Agency, but I hope it's actually just a step on the road to some of that work. I, of course, am a huge fan of that work. I just have somehow transitioned from space research and physics into shoveling mud, which I'll get into in a minute here. Hopefully it makes sense. So this will be a presentation on the quest for big mud, large-scale additive manufacturing in earth, specifically locally sourced earth, printed on site, outside, not inside a warehouse, just out in the world. So of course, first, it's always important to talk a bit about why earth is actually a material to take seriously in our modern age of concrete and carbon fiber and all of these other things. First off, over 3 billion people live and work in earthen structures every day. Many of them are complex buildings with great structural performance. This top image is actually in Germany, a somewhat recently constructed dome. Here you see 8 to 10 story housing units in Yemen, and some more contemporary modern earthen architecture that's rammed earth. So I think this is a good context to begin with. You have people all over the world who are engaging their own local materials and using their knowledge to build, quite serious architecture with a material that we don't see much in an urban setting, which I think is in large part to a failing of codes and standards for this material. So just the general overview, my work revolves around local material and the flexible, cheap tools that can be created to make it more accessible to people who can actually utilize this technology for something productive in their lives that they need. And kind of, this is a funny thing to say after these previous presentations, but my work is largely about turning this complicated thing we call a robot into a much more useful thing. We call it a tool that everybody understands. And I hope we can make a few steps towards that. So the team for most of this work that I'll be showing is Logman, Barak, Virginia, and Ron Real. We're largely associated with emerging objects. Ron and Virginia's design firm. So to begin with, a lot of this work started at a small scale, testing out whether or not it's possible to mass produce ceramic products with a ceramic 3D printer, using a variety of different materials and creating forms that are otherwise unachievable with standard industry practices like slip casting, ram press molds, that sort of work. And we were relatively successful in doing this, creating many hundreds of these cups and little espresso vessels. This is exciting because it meant that we could really think about scaling. But in order to do that, we needed to create better tools that made this technology something that everyone can use. So I encourage you to check out Potterware, which is something I've worked on for a number of years. It's basically a web-based slicing tool that allows non-technical users, people who have never used CAD before, any 3D modeling, to go in and create their own beautiful, complex object and then print it without needing any high-end computer equipment or anything like that. You just need access to a printer, of which there are now quite a number of ceramic printers. And this was a compelling study because we discovered not only do students quickly engage with and begin creating exciting, interesting objects, you can also use a wide range of materials, and the software has proven to be robust enough to handle that. So on the left here, you see part one of our Mud Frontiers project, in which students from both sides of the US-Mexico border in Juarez, El Paso, collected local earth and used our tools to 3D print their own designs. And I just found it compelling that not only was there functionality for a wide range of material, but also functionality for a wide range of aesthetics and design interests. So of course, in doing so, we also couldn't resist scaling a bit, creating our first large-scale earthen print inside, but also it was created with local earth from outside in the Texas desert here. Quickly, we had to leave the building. And so a few months later, we began printing in the field, literally, using also locally sourced earthen mixes. The one thing I'll say here is that the easiest way to do large-scale earthen material is or earthen printing is to begin with the material itself. So you look around the world and you find a place where there's large buildings made out of earth, and then you know the mud there is probably pretty good. And so you can just take your printer and start talking to people about what their ideal mix is, and then find ways to calibrate it to your robotic system, which is what we've done here. The results of this first set of work were a series of objects, the beginnings of which were rather crude, and they developed into buildings that have some serious function. We made a stair and a small enclosure where people can sit and eat and share the warmth of a fire. We can see that this is a pretty rustic process. We're not 3D printing with AI on the moon, but we are engaging what we consider to be necessary technology. So we're in the field. We have a very lightweight robotic arm that's a SCARA robot, which means it's a 3-axis robot that prints with polar coordinates. So it can make an object that is much larger than itself, which is a pretty important note here. It means that we can take a printer that can literally be picked up by one person and moved around and create a 10-ton earthen structure. Here you can see we're doing some hose management with local infrastructure, a tractor, and mixing material on site. The material itself was dug in the field right behind these images. You can see our first stair, our first attempt at a door. We began experimenting with a few things like decreasing layer height relative to slope in a domed structure to improve layer-to-layer adhesion, which a number of people do at different scales and different materials. The one thing I will say about this is it looks rather low tech, but of course, this whole system is controlled via Wi-Fi from a number of devices. So you can have one person on their phone, one person on a tablet, another person on a computer, and you can seamlessly transition between who's shoveling mud and who's controlling the machine because it's live on multiple devices at once. So we do quite a bit of work on the software end to make sure that we can handle the variability of material and pause whenever we want, go back in the print whenever we want, scale things a little bit if we're dealing with a really hot day where there's shrinkage. Um, so here you can see the most recent result of this work, a 3-part structure made during COVID last summer, with a space for sleeping, eating, and bathing. I'm sure you'll see more pictures of this soon. The interior is not quite complete yet. And it was an interesting experience to really just commit to working on site and actually just saying, all right, we're going to do this entire thing right here, regardless of the weather, with the material we can dig out of the ditch next to our site. You have to handle things like ambient humidity, which slows drying time of the earth. You have to handle when it actually starts raining. You know, can your structure handle the added weight without buckling? Ours did not fall down, luckily, but we did suffer a few rainstorms. Believe it or not, mosquitoes were probably the most challenging factor of this whole project because it would rain and we were in the middle of a cow pasture. So then we would be attacked by mosquitoes and had to engage some great local technology of burning cow dung to scare them away, which proved to be very effective. And on the actual printing side, we of course have to deal with a number of issues like, well, we didn't want to bring anything to the site, so we just used local gravel for foundation. And so despite consolidating it as much as possible, you do get some differential settlement. You have to handle the way the structures shrink relative to the solar gain. Of course, one side dries faster than the other because of the sun. And so this is something that we started to account for in our models, which I can talk more about if people have questions. And then, of course, you get mechanical issues when you're trying to print in a windy thunderstorm. But I'm happy to say that we've reduced the system to the point where it's actually largely quite effective in almost any weather, because you don't have a million extremely expensive sensors on the verge of failure at any given moment. So you can see here some of our very advanced technology. We wanted to expand the reach of our machines, so we purchased a relatively high precision 4th axis rail from the local hardware store. This is made from plywood and 2x4s, giving us the ability to set the machine in 3 positions and print about 60 centimeters at a time on each structure and then move to the next structure, which really sped up our print time. So what you see here, the image on the left, is about one afternoon's printing on a day that wasn't super hot. So we couldn't print as fast as possible, but we were able to get a decent amount done in a day. And interestingly, this quantity of kind of wall construction is very similar to what you see in earth and brick construction, because you typically only stack bricks to the point where you start getting a lot of compression in the mortar with adobe buildings. And so we're actually in a similar rhythm of construction to the traditional methodology. So of course, we also couldn't resist experimenting a bit with integrating furniture into our tool pathing. One nice thing about using local material is it's very cheap, so it's okay to make dense objects. We also began exploring, can we integrate sort of vernacular lintel technology into our structure? So here you can see we have a local piece of cedar placed inside the wall, connecting 2 of our structures here. Of course, you have to program the machine to pause in the correct moment without sending mud everywhere to place these, which was a interesting experiment in toolpathing. Go back one. So we did all this work, but a question that I'm always faced with when I look at the kind of current state of 3D printing buildings in the world is, what about the roof? We've seen a few projects that start to handle this effectively, but more often than not, you see buildings like this sort of terrible thing by the U.S. Army, where not only did they only print walls, they also had to do it inside another superstructure with a conventionally constructed roof and a conventionally constructed foundation. To me, this is sort of the kind of thing we're trying to avoid. Um, at least here, they made something really beautiful with CLS, but again, they're facing this issue of how do we enclose the structure? And so, in my own research and with my students, I've been exploring uh, ideas of covering a structure without needing formwork purely through geometry and clever toolpaths. And we're seeing more of this now. Of course, much of it is inspired by Hassan Fatih, the Egyptian architect, who revitalized some of these um, earthen construction techniques that were created in parts of the world where there's not readily available timber. So, of course, local masons came up with clever solutions to building roof structures without formwork by angling the courses of brick. Um, so here I'll show a couple of our experiments. Some of this work was a bit cut short by COVID, but even using a 3-axis machine, you can achieve pretty steep angles up to a 1:10 scale. Currently, my research is building up to full-scale construction with earthen materials, particularly in this realm of the squinch dome, which you see in the middle image. And also building the kind of structural analysis tools we need and the optimization tools we need to really validate some of this work. So you see a typical buckling failure here and some beginnings of simulation that takes into account issues of delamination. I unfortunately can't talk too much about this yet because we're in the process of publishing, but I'm happy to talk shop if anyone has questions. So of course, the long-term goal is integrating this powerful thing we get from 3D printing, which is geometric freedom and really careful attenuation of surface and texture at a minimal cost, right? Like you can make a smooth object and a varied object for similar amounts of money and similar amounts of material and similar amounts of time, which is not true in many conventional construction methodologies. So taking that and combining it with this vernacular knowledge of earthen construction all over the world and creating highly functional enclosed structures. So I will leave it there. Thank you so much, and I look forward to your questions.
Thank you very much. Very interesting to see. Yeah, so my initial question is you talked a little bit about the not having expensive sensors, but do you have a sort of a goal for achieving a certain degree of automation, or are you more looking into the what is possible with 3D printing rammed earth?
So I would say on a personal level, I'm very interested in integrating more automation, but from a as pragmatic a standpoint as possible, right? So if you look at a tractor, right, it's a great tool and it has a few really useful sensors. Like it tells you when it's almost out of gas, right? To me, that kind of sensing is very compelling and very applicable across the board. And I think there is some potential for that here, of course, and we see it in many large-scale concrete printing projects. But I often question what is going to be the most useful set of sensing tools. Like, do we sense differential settlement? Do we sense the water content of the earth that's a few layers down? And what I've been finding is that a lot of this can actually be like integrated into the software end. So where I'm focused is building really good tool pathing software that can take some input material parameters, because the problem is the material is always different. So all of these examples we showed, we had to adjust the mix, right? And the reason it was possible to make these things is because as a team, we have broad material knowledge of earth. So I've worked as a glaze chemist and in a tile factory. Ron Real grew up building earthen buildings from Adobe brick. My colleague Logman is from Sudan, where he grew up working in a different earthen construction methodology. So we had a lot of knowledge on, okay, how much straw do we add to this earth, right? And so finding ways to actually calibrate that and creating standards to test for that, I think will do a lot more for the progress of this work than necessarily building in onboard sensing. So if we can really take on the material properties at the beginning of a project and say, okay, this is how this works, bring it into the model, I think we'll see a lot of improvements.
Thanks. Yeah, and maybe I'm trying to make the connection too much with the previous speaker, but I think you're both on although it's seemingly very far off on the spectrum of 3D printing on Earth in a very simplest manner, and on space very high tech. But in when I see your type of printing and the way you think out of solutions, keeping it simple, finding pragmatic software solutions to solve these kind of problems, do you see any of your innovations finding an application in yeah, building structures in space?
I mean, absolutely. I think I'm certainly one of those people who dreams of getting to design structures for space, and I think it's there is an obvious connection because on space we're not going to bring all the material we need to build something, right? That would be crazy. Um, and you also need, especially on the moon, you need a ton of radiation shielding, which requires just a ton of material. And so obviously we're going to have to do something with lunar regolith, right? Um, as we saw in the previous presentation. And so I think that's in part why I have so much interest in building out really intelligent software tools that are really focused on material. So understanding how to build, you know, like layer adhesion and these kind of binding properties into a model that looks at the delamination between layers, all that kind of thing, I find really compelling for the future because, the Earth itself is an amazing test bed for building up the material knowledge and the material flexibility we need to make this technology like kind of as good as the shovel, like I was saying, right? Like right now, printing systems are for the most part very specific. You need a really good mix. If the mix isn't dialed in, you just get this giant mess. Um, and so, but if you have five guys with some knowledge of the mud, they can build anything with their hands, right? And so I think it's finding some software that bridges that gap.
Nice, thanks. So, a question from the audience, Dr. Nestle. He has a question whether, yeah, if you can explain a bit what the differences in material properties and behavior of the earthen materials and cementous
Sure.
materials are.
So, so generally speaking, um, I'll set rammed earth aside for a minute because that's a bit different. This isn't compressed earth we're printing with, but generally speaking, the structures we're making and most earthen buildings. I should really know what it is in metric units, but it can withstand about 300 pounds per square inch of loading, which is quite a decent amount when it's dry. And as you saw in the very first slide, there are 10-story structures on Earth that are made entirely from local soil. So I would say that strength is less the issue. The issue is that you can't reinforce earth in quite the same way as some of these cementitious materials. So when you see these 3D printed concrete projects, where I get excited about them is watching how like the full range of concrete building technology gets implemented in a 3D printing system where you start to integrate rebar and integrate that sort of thing. So I would say that's a major difference. The other huge upside of printing with earth over cement is that it doesn't destroy your equipment. Um, if something goes wrong, there's a big thunderstorm and you have to go inside. Like when you come out, your gazillions of dollars of equipment isn't done for because you left some cement cure. And on a similar note, I actually see that as a huge advantage because obviously one of the really big problems of concrete construction is the life cycle of the material and the life cycle of the buildings. Most buildings made out of concrete, they're not built to exist for more than 50 or maybe 100 years. but the material will be really difficult to manage for far beyond that. Whereas with earthen construction, there are structures that are 1,000 years old that are still standing, but if we want to, we can dismantle them relatively easily without a huge impact on the environment. And so I think if we be more realistic about what the life cycle of the buildings we make actually is, earth becomes a super compelling material.
All right. So last question from Dr. Nessel. He maybe it becomes less compelling but his question is: do you need or think about using additives or conditioners that make earth printing easier?
Yes, so that's what a lot of my my current research kind of gets into, because there are some modern material science kind of things we can do to our material that are not horrible for the environment and not hugely material intensive, that can really improve the strength. So, of course, right now the main additive to this material is straw, which is a traditional additive. Though people often misunderstand its function, it's not to add strength; it's actually to wick moisture out of the wall structure more evenly, so you get less cracking and more even shrinkage as the building dries. But yeah, I think a lot about what we can put into the mud to make it a little stronger, a little more capable of, sloping structures, ways to minimize water content, right? And there's a lot of transferable technology from especially industrial ceramics that we can think about here.
All right. Thanks. So that concludes, I think, all the sessions of today. Oliver, do you want to pick up from here?
Yeah, guys, thank you very much. And thank you very much, Chiara and Sandy, for this very impressive talks.